Today's lesson is on 8.3% yield. So good evening, everyone. So we are in the last subchapter of Unit 2 this evening. It's a very short lesson. In fact, it really just carries over from what we've done in 8.1 and 8.2. Remember that in 8.1, we looked at stoichiometry. Okay, and in 8.2, we looked at limiting reactants. Okay, so in stoichiometry, typically you're only given, let's say, the mass or the moles of one thing. In a limiting reactants question, however, you will be given the mass or moles of all your reactants. Okay, so whatever reactants you have, that's what's going to be what you're going to see in terms of the numbers given to you in a question. Okay, so please make sure you know the difference. Okay, especially for the test. Let's move on. So, chemists use stoichiometry to predict the amount of product that can be expected from a chemical reaction. So, whenever you're being asked to find the mass of something, okay, technically, so think back at 8.1, 8.2, anytime I've asked you to find the mass, you have been technically calculating what is referred to as the theoretical yield. So the theoretical yield is a fancy term for the mass calculations. Okay, so the mass calculations in a stoichiometric problem or a limiting reactant problem. Okay, that's really what the theoretical yield is. So if I ever ask you what is the theoretical yield, so it might say, what is the theoretical yield of carbon dioxide, right? If that happens to be one of the products. So you're going to find the mass of carbon dioxide. So don't let this term fool you into thinking, oh, what is the theoretical yield? The theoretical yield, like I said, is just a fancy term for finding the mass as we did in 8.1 and 8.2. Now, we have another definition here to make note of, and that's the actual yield. And so the actual yield, okay, on the other hand, is what you would find in a chemistry lab. So in a lab scenario, you would be calculating the actual yield. So what you would be doing, right, mathematically is comparing, okay? So you're going to compare the actual yield, right, with your experiment, right, with your trial runs, and comparing it with what you would get using stoichiometric problem solving. Okay, so once you let's say in a lab scenario, you can compare the two. And what you want to be able to see is how close is what you find in a lab to what you actually get. What you calculate to what you actually get in a lab scenario. Okay, so the actual yield of chemical reactions is usually less than the theoretical yield. Okay, so understand that the actual yield is always going to be less, right? Because the thing is that there's always going to be errors that you're going to make. Sometimes it could be more, and typically if it's more, there's major mistakes that you've done in the lab. Okay, but for the most part, the actual yield should always be less than the theoretical yield. Because remember, the theoretical yield doesn't take into account errors. It doesn't take into account other problems that can arise while doing your experiment. Okay, so another thing that can occur, or part of the reason why you're not going to get the same results is that collection techniques can result in lower than expected yields. Okay, another factor, so that's one factor. A second factor is that there could be what is referred to as a competing reaction. What that means is, as your chemical reaction takes place, you're forming a product. That product, for some reason, has some kind of chemical reaction with one of the reactants. So as you're making the product, that product further undergoes a secondary reaction. And that secondary reaction is what is referred to as that competing reaction. So we're going to see an example of this competing reaction here. So here's an example of a competing reaction. So let's say in a lab you were combining phosphorus, solid phosphorus, with chlorine gas, and you're forming phosphorus trichloride liquid. Okay, but as you are making this, notice now, here I'm going to write it in green, notice how there's a second reaction that's taking place. So this second reaction that's taking place is using the product that we just made, that we're trying to make, and it's further reacting with one of the reactants from this initial reaction. So that's what we refer, and look at, we're forming a completely different product now. So all of a sudden, as we are trying to make this is being, in fact, further broken down and being made into something else because of this competing reaction. So in chemistry, when working in a lab scenario, and if you're hired to be, let's say, a chemist to work in a lab, you're devising these scenarios, right? So you're not going into a job and they're going to hand you, okay, here you go, this is how we do it. This is how they're going to be like, okay, this is what we need made. How do we make it? So what do you know? What chemistry knowledge do you have to bring in and help us create this? And while you're doing this, you got to keep in mind, okay, well, I'm trying to produce this. Will a competing reaction, in fact, take place with what I am making? Okay, so let's move on. So the next slide just kind of goes through everything that I just explained. So all of a sudden, not all the phosphorus is converted to the phosphorus trichloride that we want, right? Because of that secondary reaction, which will result in a lower actual yield of this PCl3. So this PCl3 is going to have a lower actual result because of that secondary reaction that's taking place. So I'm going to introduce a new equation, and this new equation is the percentage yield, or the percent yield. So the percent yield takes into account the mass of the actual yield, so the actual mass that you're going to get, with the stoichiometric mass that you're going to be calculating. Okay, so many questions, if you look at some of the sample problems, the homework questions that I give in chapter 8, you will see I will give this mass, but ask you to find that mass. But it's not really asking you to find this actual yield. I'm actually, in fact, asking you to find the theoretical yield. And you'll understand what I mean when we look at the sample problem. Okay, so actually I want to go to that sample problem first. So that's actually sample problem number 2. So here we have, upon heating, sodium metal combines with chlorine gas to form solid sodium chloride. If 8.30 grams of sodium and 14.0 grams of chlorine are heated together, a total of 19.5 grams of sodium chloride is isolated. Determine the percent yield of sodium chloride. But all of a sudden it's like, wait a second, trying to find the percent yield. Here's a mass. What am I going to do? Well, what we're doing in this example is, let's actually, so when we're putting together this equation, you put together this equation. This is the mass of one of the reactants. This is the mass of the other reactant. Hint, hint, this is a limiting reaction question, okay, because I'm going to have two masses. And I'm going to be asked to find really sodium chloride. But this mass here, this mass is to be used at the end when we are using this equation. So this number here, this 19.5 grams, in fact, would be there. So what we're going to be finding out here is that theoretical mass of sodium chloride. So using our limiting reactant rules, we're going to find the mass or the possible mass that we can make of sodium chloride, and using that mass take this number divided by the mass that we're going to get, that we're going to calculate. That mass should be higher than the actual. Remember what we said, actual is typically lower. You're not going to have a percentage yield over 100. And you will divide them. But we'll look at the actual problems itself. Sample problem number 1, nice and simple. Let's actually look at it. So if we've got 185 grams of lead 2 sulfide was actually obtained in a reaction for which the theoretical yield was 239 grams, calculate the percent yield. So you start off with the equation, and so here we have the actual divided by theoretical. Another way to say the theoretical, the mathematical. Okay, so so if you want, you can rewrite this and go actual divided by the stoichiometry. It's up to you. You can use that if it'll help you remember how to go about solving it. But anyhow, we've got the 185 grams divided by 239 grams multiplied by 100, and we get a full value of this. We have 3 significant digits in our question, so we want 3 significant digits in our answer. So the answer works out to 77.4% yield. Okay, so the yield's not too bad, but ideally for companies, they want to try to reach as close to 100% as possible, because it is a loss of reactants. Okay, so it costs money. Okay, so for companies, who are looking for their bottom line, right? Their money that they're going to make, their profits, they're going to want a yield as high as possible. And as a chemist, you're going to have to explain why there is no way possible to be able to get a yield any closer than, let's say, this, if in fact this was something that you were working on in the lab. Okay, and a lot of times they'll hire various teams to see who's going to get the highest percent yield. And that eventually becomes the team that gets contracted to be the chemist for whatever company, so that they can help maximize their bottom line, right? If you come in, as a chemist and you're not able to reach, but someone else can, well, they'd rather hire the person who's going to help them make more money. Let's look at that sample problem 2 that we were talking about. A lot of calculations here. Okay, so let's look at what we do. Step number 1 is the equation, balanced chemical equation. Step number 2, you're going to want to list the information, and I like to list it right underneath. The one difference is I actually will put the mass of the actual above whatever product I'm being asked to find. That's just me. Okay, that's me. That's how I go about solving these questions. Okay, so it's up to you. You'll see it. This is what I do for my in my homework. So you'll see in my homework very detailed answers. So we've got the mass, right? The initial mass that was given here for sodium, 8.3 grams, 14.0 grams. There's your hint that this is a limiting reactant question, which means you are going to have to find the number of moles for both of those reactants, okay? And ahead of time, you might want to find the molar mass of your product. Remember to use my periodic table. So we devised this table. This table is just the ratios. Understand that this is the showing of the work. You can do it other ways. So I saw some students, when they were handing in the sample problem for me, they wrote down these ratios, these calculations, not using my table. They used the standard, how to calculate ratios. That's fine, right? That's the math, right? So whatever way you are comfortable with, that's how I want you to show the work, but show me the work, okay? I don't want to see you go from this straight to this without seeing all the in between. So anyhow, we want to see how much possible NaCl will sodium make, how much NaCl will chlorine make. And that's what the two tables here are. Notice my unknown is sodium chloride is my unknown. So I take the number of moles from here, and it's a 2-to-2 ratio. So the number of moles don't really change, okay, between to Na and NaCl. So Na in terms of how much NaCl can chlorine make, NaCl is actually going to make slightly more sodium chloride. So we're never going to hit this number. This reaction stops once we run out of sodium, because sodium makes the least amount of this NaCl product. Okay, so we're going to use this full number. We're not rounding, but remember, you don't have to show me all these numbers. I like to show them for you so you see how is your calculator in terms of your calculator. Are you typing in the correct numbers, and are you getting these results? Remember, and some of you were doing the ... method. That's fine. Okay, just use that ... method because it lets me know you've not rounded any of the numbers. Anyhow, we go in here, we find the mass, and this is theo, so theoretical, moles times molar mass. So we take the moles that we calculated, the least number of moles that we've made, with the molar mass, and we get 21.0983. So we get this one big number. Do not round this number either. We're not done yet. This is not what I'm being asked to find. We are being asked to find the percent yield. So we are going to substitute this entire number into this percent yield problem. So once we do that, we get this big long number. Understand that if you round this number, you're going to get a different percent yield. Okay, so please don't round until the very, very end. There'll be times where you can round, and only if you do the homework will you know when I round and when you don't, when you can round, use a rounded number. Okay, if this was a part A, part B question, and part A asked me what is the mass, then I would round this number. And if part B asks me find the percent yield, I could, in fact, either use this full number or I could round, right? I could use the rounded number from part A to help me answer part B. Okay, so understand that that's the only time you could use a rounded number if you're being asked to find the percent yield from a part A question. Okay, because technically it was never really part of the part B question, but you'll see it if you do the homework questions. See what I mean? Anyway, so the answer works out to 92.4%. Very good percent yield. It means that whatever the lab scenario was to create that was a very good, would give us very good results. I would probably test out to see, in chemistry, typically you don't want to do just one trial run. You want to do multiple trials in the event that maybe you made a mistake. Moving on to the last sample problem. Calcium carbonate can be thermally decomposed to calcium oxide and carbon dioxide. Under certain conditions, this reaction proceeds with a 92.4% yield of calcium oxide. How many grams of calcium oxide can the chemist expect to obtain if 12.4 grams of calcium carbonate is heated? Here's the thing. Students have a tendency to panic when questions are longer than a sentence or two. Okay, so don't let the size of a question or how many lines a question panic you. Break it down into steps. See what the question asks. The first sentence tells us the reaction. The second question just tells us we get a yield of that high. Okay, and the third part It's asking us to find the mass of calcium oxide, if I'm given a mass of my reactant. Okay, so this is a regular stoichiometry problem. We find the mass. It's a 1-to-1 ratio. And so that the number of moles is the same. So we take that number of moles, multiply it by the molar mass of calcium oxide, and we're going to get this 6.94. So we get this big, long mass. Okay, remember, we're not done here. We are being asked to find how many grams of the calcium oxide can the chemist expect. This is the theoretical yield. We're being asked to find the actual. We're not in a lab, but mathematically we could find the actual if we are given the percent yield. Okay, and in fact, in this question, we're given the percent yield. So the percent yield is our given. The only one that we're being asked to find is the actual. We just calculated the theoretical. Isolate your actual, and in the end, it works out to this mass, 6.4196444 grams, which we finally, this is the only number we round. We round the number to 6.42 grams. Okay. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.